Hello, I'm Katie Steckles.
And I'm Peter Rowlett, and hi Katie, what's today's mathematical object?
Today's mathematical object, as some of our listeners may think is fairly long overdue, is a Battenberg cake.
Yeah.
Which I believe, we've been doing this podcast for a very long time now. I suspect we've probably mentioned some of the ideas that we're going to talk about in this podcast before, but not really kind of properly covered it yet. So I've brought a Battenberg cake, partly because I like cake, but also because there is a really nice mathematical structure encoded in this cake. So for the benefit of anyone who, I guess, didn't grow up in a country where Battenberg cake was de rigueur, Battenberg is a traditional cuboidal square cross-section cake, which has a layer of marzipan wrapped around the outside for reasons that no one can fathom, and inside there are 4 different square cuboidal sections of cake, which are arranged this is like a ludicrous description of a physical object, but basically there's 4 bits of cake that kind of sit in a little square, and the top left and bottom right are yellow cake, and the top right and bottom left are pink cake.
Unless you rotate it.
Unless you rotate it around, in which case they'll be in a slightly different configuration, but in some orientations it's yellow in the top left and bottom right and pink in the top right and bottom left, and no one knows whether the 2 different cakes are different flavours. They're just pink and yellow. It's the whole cake is a mystery to everyone, but it is a very long square cross-section cake, which is very traditional and presumably has some historical origins, but I'm not a cake historian, so...
No, the name Battenberg. It's one of those things that you've known since you were a kid, so you don't really question it. But presumably there's something behind that and why it's called that. Yeah. So I've done a bit of hasty searching on Wikipedia. It says, while the cake originates in England, its exact origins are unclear.
Because it's very long and you can't see the far end of it. Yeah.
Early recipes refer to it as domino cake and Neapolitan roll and church window cake.
Ooh.
Anyway, apparently named in honour of the marriage of Princess Victoria, a granddaughter of Queen Victoria, to Prince Louis of Battenberg in 1884. He's of Battenberg, the German town, and it talks here about who then inherited the title, and this eventually ends up with the Mountbattens.
Ah.
It's the same Batten in Battenberg and Mountbatten, apparently.
Right. That's good. Like a lot of people have a cake at their wedding, but they don't necessarily have a cake that was created specifically for and named after their wedding. That's a real honour if there's an entirely new type of cake that's been conceived just for your wedding.
It's pretty special. It says the first cake was baked in 1884 to celebrate the wedding. It's Prince Louis of Battenberg marrying Princess Victoria, who is Queen Victoria's granddaughter and Prince Philip's grandmother.
Right. Could they not have just done a Victoria sponge? Seems like too much effort.
And it also says here that the large checkered patterns on emergency vehicles in the UK are officially referred to as Battenberg markings.
Ooh.
Because of their resemblance to the cake.
Nice.
Yeah.
That is good. But the reason why it is a mathematical object, and this is something which I think probably other people have talked about this, I think Eugenia Cheng has done some stuff about this as well, is because it has a really nice structure, this sort of diagonal pairs of colours, which can be used to describe a mathematical group. And in order to contextualise that, I guess, we can start from the very basics of groups. So this is it's one of those wonderful things that is actually a brilliant and important part of maths at university. But if you study maths at school, you will never meet this. And you'll never even think of this as being part of maths, but it's sort of an abstract structure. And luckily, there are lots of nice concrete examples that we can use to make sense of it. So a group is a bunch of things, as the name implies. In fact, I asked one of my students this morning, what do we know about groups? And they said they've got to have more than one thing in them. So, well, actually, they don't, because you can have a one-element group, but good try. I think they were thinking of the sort of colloquial definition of a group.
A group of people, yes.
So, yeah, technically, I guess a group of people requires more than one person, but in maths, a group can have any number of elements, we call them elements, the objects within the group. And the thing that makes it a group, as opposed to just a set of things, is that it has some kind of I guess a combining rule is a good way to describe it. So if I take two things from the group, I can smash them into each other, and the result of doing that will be another thing from the group. So a kind of obvious mathematical example of this would be numbers. If you've got whole numbers, I can take two whole numbers, and let's say my combining operation in that case is adding. I can add those two whole numbers together, and assuming I've done it right, I will get another whole number. And there is a sort of group structure there which behaves itself. It's got various... the sort of combining rule has to have a little bit of well-behavedness to it. So things like if you combine two things and then combine that with a third thing, it doesn't matter whether you do... I'm going to phrase this carefully because I'm not going to say it doesn't matter what order you do that in, because it does sometimes. But if you say you've got A and B and you combine them together and then you combine that with C, you get the same thing as if you combined B with C and then combined A with that, if that makes sense. So this is called associative, but it basically means brackets. You can move the brackets around because you've only got this one instruction. So the main place where brackets become an issue is when you're doing things like multiplication and addition. But if you've just got this one type of thing that you're allowed to do, the brackets don't kind of necessarily matter or change how it works. There will be, in the group, there will be one unique thing which is special, which we call the identity element of the group, and it's kind of the nothing-y thing, the thing that doesn't do anything. So I'm sure some people are wondering how this is going to relate to Battenberg cake, but we'll get there. So in the group of numbers, if you've got adding 0, I guess, would be the nothing-y thing, because if you add 0 to something or you add something to 0, you still get the thing that you started with. And this is, feels like completely unimportant, trivial thing, but actually it is kind of crucial because it allows us to define inverses in the group. So in terms of numbers, you've got negative numbers. And if I've got a number like 4, the inverse of 4 is in there, it's -4. And if you add 4 and -4, you get back to 0.
You get the identity.
You get back to the identity. So, the context of numbers is a sort of nice familiar one, but you can apply this structure to lots of other stuff as well. So you could do, for example, numbers restricted to a finite set of numbers. If you imagine the face of a clock, this is a classic example of a group that people often talk about. So the face of the clock has got the numbers 1 to 12 on it. And if you add numbers, I'm doing finger quotes here for anyone who's listening to a podcast, but if you quote unquote add these numbers together, you have to kind of use a special version of adding where you wrap around the clock. But if you say added 4 hours to 11, you would get 3 o'clock. And this is kind of consistent, it works. You can add any two numbers of hours together and get a number on the clock because you just keep wrapping around. And this is sometimes called clock arithmetic or modular arithmetic. But this again has the structure of a group, and there's an identity in there which is 0 or 12 o'clock. 0 o'clock when you have lunch. And if you add 0 hours to something, you get the number of hours that you started. But if you add 4 hours and -4 hours, you get back to 0. So all of this sounds fairly pointless because we just know how these things work, but you can apply the same ideas to... There's a huge number of different structures that have this kind of idea behind them. And so, for example, permutations is a nice example. So this is ways of rearranging sets of objects. And in that case, you have an underlying set, which is, whatever your things are that you're permuting around. The group is then the possible ways to reorder the objects. And it's interesting because you don't think of that as a thing, but it is a thing, right? The particular pattern of reordering is an object in the group. If you combine two of those, what you essentially do is take the original set of things, reorder them using the first one, and then reorder that set again using the second one. So you're kind of combining the two reorderings, the two shuffles, to get a different shuffle, which will also be a valid shuffle.
And the identity?
The identity is not shuffling anything, leaving everything exactly where it is. This is the thing, for any group you can ask these questions. What's the identity? What does it mean to have an inverse? So the inverse of a particular reordering is just putting everything back. The kind of the putting things where they previously were.
Which is why the identity is doing nothing. Yeah. But I love these groups where it's I will now perform the identity operation of this group.
Yes.
Does nothing.
Yeah, adding 0.
Yes.
It's all good stuff, and like I say, it feels a bit pointless, but the reason it's there is to kind of make sense of the inverse things, so that you've got somewhere to come back to. But also, a lot of the time when you're playing around with groups, you can kind of show that something is the identity. That tells you something interesting about that object. the thing about groups is they come in all different sizes. And I happen to know this because when I was at uni, I hung around with a lot of people who studied very big finite groups. So there are infinite groups, there are finite groups. Some of the finite groups are absolutely massive, like huge numbers of elements. And in fact, a lot of the maths at that level is kind of computing what happens when you multiply different things together within the group, and the different kind of subgroups, I guess you can call them subgroups, that have different properties and that sort of thing. And there's a whole bunch of nice other properties that groups can have, but they are generally just a really nice, useful way to model things in the real world. And the thing that I like about Battenberg cake is actually it's not a thing that you can model with a group, it's actually a thing that models a group, right? So you've got this structure. If you're picturing a Battenberg cake now, if you're either looking at a picture of a Battenberg cake or a real Battenberg cake, in which case, well done, but wait, don't eat it yet because you need to look at it first, or just imagining it. So you've got a yellow square in the bottom left and top right, and a pink square in the top right and bottom left. This is basically the kind of diagram that you would draw to understand the structure of a group. And the group that we're talking about here is one of the simplest groups, which is the group with two elements. Okay, and because these are sort of abstract ideas, you can kind of call them whatever you want, but I guess for simplicity we could think of them as being 0 and 1. Okay, so 0 and 1 are the two, and we think of them as numbers, in which case we can think of the operation as being adding, I guess, and we're working on a clock that's just got the numbers 0 and 1 on it, so if you get to 2, you wrap back round to 0.
Right.
So you're only allowed to have 0 or 1, 2 equals 0, 3 equals 1, and so on. So if you put those across if you imagine writing them across the top edge of your Battenberg, so 0 in the left column, 1 in the right column, and down the left-hand side you've got 0 on the top row and 1 on the bottom row.
So it's like you're making a multiplication table.
Yeah, this is essentially a multiplication table just for this group. Mm-hmm. And this is quite often a nice way to encode the structure of a group because, you know, in some cases the operation, the rule for the group is just a known thing like multiplication or addition or combining permutations or whatever. But sometimes you just decide what the operation is and you define it using the multiplication table. Mm. So that will, in very many ways, define the entire group itself. And the Battenberg cake encodes this very nicely because 0 plus 0 is 0, which is yellow cake, in our analogy. 0 plus 1 is pink cake, which is 1. And then 1 plus 0 is also 1, which is pink cake. And 1 plus 1 is 2, which is 0, which is yellow cake. Mm-hmm. So it's actually got this structure built into the cake there. And it's actually, even though it's really simple, there's something elegant, there's something nice and symmetrical about this. But actually there is something nice and symmetrical about this group. And it's called Z2. It's got, you know, lots of mathematical properties. It comes up a lot in working with binary numbers. Yeah. You know, it's the underlying group that exists behind all of binary and all of computer science stuff.
It's XOR, isn't it?
It's kind of the exclusive OR operation is, in some sense that's defines the operation a little bit. So it's plus or it's XOR or it's binary addition or whatever, whatever you want to call it. And yeah, there's a cake, and I'm pretty sure the people who invented the cake weren't thinking about group theory when they did it. But it's just lovely. And the obvious next question, of course, is what happens if we built a cake for a different multiplication table? And for this, I will reference the standard reference for Mathematical Bakery, which is the Maths Jam Bake-Off competition. Yep. So the Maths Jam conference, which happens every year in the UK, we have a bake-off. I don't know why we have a bake-off. I can't remember how it started. There was just a bake-off suddenly. And people would bring in mathematical bakes, I guess. Mm-hmm. And one of my favourites that's ever been was someone who did a Battenberg, and I think it was like a 6x6 square or some ridiculous number of different very long, thin square tubes of cake arranged into a 6x6 grid. But they had 6 different flavours of cake representing the numbers between 0 and 5. And you can do the same thing with this. So, you know, you do... 2 times 4 is 8, but because you've only got 6, you wrap that back round to 2, and so on. And this is modulo 6, I guess, or modular arithmetic. But it's also a nice little group, and it's got 6 elements, and the 6 elements interact in the specific way as defined by this ridiculous cake that someone had made.
And this is a Cayley table, right?
So Arthur Cayley was one of the big names in early group theory, and a Cayley table basically just describes how the group works, how all the elements interact with each other. Because in order for it to be a group, you've got one operation that you can do, and it takes two things from the group. The result is always another element from the group, and it behaves well with respect to these things. So the identity is always the identity, and what have you. So the first row of the table is always just what happens when you put the identity in front, and the first column is what happens when you put the identity afterwards, and it's just the list of things again. And then beyond that it gets more interesting, and the diagonal is also interesting, because what happens if you multiply an element by itself? What's the square of an element in a group? And there's all kinds of related notions, like what power do you have to raise an element to, which is in itself is a weird question, because when you say raising to a power, in terms of numbers, that feels sensible. But if the thing that you're doing is like combining permutations or some other slightly weirdly defined thing, it's just doing that a lot of times.
And it feels sensible if it's multiplication, but if your group, even with numbers, if your group operation is addition, you can still talk about raising it to a power.
So you raise it to a power, again doing finger quotes there, you quote unquote raise the number to a power by just repeating the operation that many times. How many times do you have to do that before you get back to the identity? Because for any element there will be a number that is the case for. It will be a number which is a factor of the number of elements in the group. Nice little fact, nice little group structure fact. This is all coming back to me. This is like the kind of fundamentals of group theory. But it is just this sort of deeply abstract idea, because all of these things work in exactly the same way in all these different applications. But it just sits there and does its thing, and I like groups. And
like you say, it's a little bit like things like complex numbers. It's one of those things that's absolutely huge, but no one's heard of it. Because it's not in the schools. I do wonder sometimes if you could play around with this stuff in primary school, because there's a lot of very simple examples that you could bash together. You could play with these tables. You could eat cake. Like, it's win-win. You learn how to tell the time.
Exactly. You learn this stuff, and you learn that if you go past 12 o'clock, it wraps back round. But you don't necessarily think about the sort of underlying structure there. And there's a lot we can learn from sort of the way of mathematical thinking where you have an abstract version of something. Because once you understand how the structure works on a particular example, you can abstract it up to this notional version and then apply that to anything else that's got the exact same structure. And this is why group theory is so incredibly powerful. And a lot of the time, if mathematicians are working on things that are like, oh, this is a group, they're just great, we'll get the book out, we'll get the known list of facts about groups, and we can use all the tools that group theorists have developed with this. So it's very nice, and a delicious cake.
So we're both on Twitter and Mastodon. I'm at Peter Rowlett.
And I'm at Steckles. And on Twitter the podcast is at MathsObjects.
We both blog at a website called aperiodical.com, where you can find more episodes of this podcast.
And if you have any thoughts or any comments or any suggestions for objects that you would like us to talk about in future, you can email objects@aperiodical.com.
The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.